Okay, so welcome to our last learning experience before AP exam prep. This particular lesson is going to really be jam-packed. Most of it is going to be based on what we looked at yesterday with that movie clip and talking about resonance. But then we are going to add two other special topics that might appear on the AP exam. So I figured I would throw them in here. We'll go over them really, really quick and kind of put wraps on waves and sound. So yesterday we saw a movie. I told you that there were two main vocabulary words that were emphasized there, and the examples in the movie were outstanding, although you guys are pretty sharp. I'm sure you picked up right away that some of that video was pretty vintage. So even though they were old examples, they were still very, very good examples, right? First term that we looked at yesterday a little bit was natural frequency. Now, natural frequencies are, in a lot of cases, several frequencies that an object would tend to vibrate at that are based on, what the object's made out of, structurally, how the object's put together. All of that stuff kind of combines to provide us with a set of frequencies that, would allow the object to vibrate freely. If you were paying attention in the video, you saw the Caltech professor that had the beaker with the speaker really close to it, tuning in the frequency, right? What was he trying to do? He was trying to dial in a natural frequency of that beaker. So as he was moving the frequency of the sound wave around, he got it so it was just right, and the beaker began to shake more violently. Then when he turned up the volume, he shook it so violently that it structurally failed and broke, right? Now that can happen to a variety of different objects, right? We saw the building structures and how those, we had three different examples, exactly the same square footage, but they were put together differently, they were shaped differently, they were subjected to frequencies that would be typical of an earthquake. One of them was shaking violently, the other two, not at all. So if you're an architect and you're putting together a building that's going to go in an area like in California where there's a significant, there's a higher rate of earthquakes because of the way the soil is, the way the earth is in that area, you would probably want to pay attention to that, right? Because some structures will be a lot more susceptible to toppling based on their natural frequency. Resonance. Resonance is the force vibration of an object at one of its natural frequencies. So, we're going to shift our focus of resonance and resonant vibrations and all of that to musical instruments, but not really musical instruments in particular, because we're going to categorize that a little bit better. I did want to make note of the fact that sometimes, a lot of times we try to eliminate resonance, right? We saw the example of the Tacoma Narrows Bridge, which was a tragic example of resonance, but in some cases, in a lot of cases, and it was highlighted in the video, resonance is a good thing, right? You look at the board here, it says, the best of the best musical instruments are defined by, and you pay for them because of, their ability to resonate and resonate well. So the better the resonant properties of the materials that are used, the more expensive sometimes those musical instruments will be. And musical instruments, we want them to vibrate at a whole bunch of different natural frequencies, right? We want them to have a lot of natural frequencies. They have to have them so that they match all of the notes on the scale, right? So that all of those notes can be resonating through the columns. Okay, so as we look at how we're going to break this down, we are going to simplify how musical instruments are created based on two categories, open pipes and closed pipes. I'm not even going to define them. I'm just going to ask you guys, just by thinking what you know about musical instruments, to give me some examples of each before we go ahead and go and do a definition. What do you think examples of open-piped instruments would be?
A clarinet.
A clarinet. I'll write it down. Any others? What? Sax. Good enough. Trumpet, trombone. We'll get tuba. We'll get to how we went from the examples to a definition shortly. What about closed end? These are a little bit harder to identify. Good. A bell. Okay.
You didn't even give us a shot on that. At least it was going to
Hey,
be piano.
we've got valuable video getting burned up here. So you guys did a great job. We identified open and closed. So now let's try to get definitions down. What do you think what should the definition be for an open-ended or an open pipe instrument? Air comes in one side and goes out the other side, right? So we've got a pipe that's open on both ends. Closed, everything's happening on the same side of the instrument, right? So we're creating the vibrations on the same side that they're being projected from. Does everyone agree? So it usually requires something like a soundboard, like a drum has the head on it. A guitar has that soundboard on top with the bridge attached to it that makes the entire soundboard shake. And I'm going to show you examples of all of this stuff here shortly. We have quite a bit of show and tell type stuff to do today. So open and closed pipes. Let's start with open. Actually, let's do a general thing. For all musical instruments, for all categories, what kind of wave are we talking about that happens in a musical instrument? We already talked about this. What are those called? What do all musical instruments use? What? Standing waves. Excellent. Standing waves. Standing waves have two anatomical parts to them, right? One starts with an N, the other one starts with an A. What are those? Nodes and antinodes. Awesome. All of that stuff is going to be useful today. If we didn't do that lesson first, we couldn't do what we're doing today. Because nodes and antinodes become extremely important when we're trying to understand how musical instruments work. Now, in order for me to create a standing wave in something like this trumpet, I can't just push air through this mouthpiece. Does everyone agree? Is that going to allow me to play a note? This is going to prove to us that we need a standing wave, right? So we have both of our lips vibrating. They're going to create a bunch of different waves, a whole bunch of waves of the same frequency that are going to occupy the same space. Remember the definition of a standing wave? We can do that is to do what to this mouthpiece? What do we have to do? We have to buzz our lips. We're going to have to create vibrations with both lips that are going to go into this mouthpiece then and create the standing wave that we need. So it'll sound like this. Instead of, if I just blow, I don't get a sound. If I buzz my lips, I get a sound. Now, when you buzz your lips, you're creating a standing wave. When that standing wave has an antinode that's aligned with the end of the pipe, all of the air in the column is going to start to resonate the metal of the pipe and all of the air inside of it. So you get an amplified effect. Now, does everyone understand that so far? No big deal, right? For open pipes, the amplitude of the actual, the amplitude of the wave, or where the antinode would line up, the first time that that's going to happen is the way I have it shown here. So here's where I put my mouth, and I create the standing wave. Here's the end of the pipe. This is the length of the pipe here. The end of the pipe is here, so I've got my antinode lined up. How much of a wave is this? Look at the picture. How much of a wave is that? It's half of a wave. So, and does everyone agree that I couldn't, there's no antinode closer that I could have aligned, right? So the absolute lowest note that I could produce is one where the wavelength of that wave is equal to half of a total wave. So the length of the pipe represents half lambda. The note that we're talking about there is called the fundamental frequency. There is a lowest note for every length of pipe that you can play. Those of you that play a brass instrument, you guys know what I'm talking about, right? So each one of the fingerings on your instrument, all the fingers, does everyone know what the fingers do on an instrument? Like a trumpet. So I press these buttons. What does that do?
Doesn't it close other?
Good. It closes some of these pipes, opens others, depending on which fingerings you have. And all that does in turn is give you a different length of pipe. It's a lot easier to see it when the trombone's doing it, right? When the trombone is doing it, you can physically see him increasing or decreasing the length of the pipe because he's moving a slide. With this, we're doing the same thing. We're just doing it with the buttons where we're saying, you know, this air passage is going to be open, this one's going to be closed, so then you've got X as your length. If I change the fingering, I change the length of the pipe. So, but for any given length of pipe, there is going to be a lowest frequency. That's going to be when you have half of a wave lined up with the end of the length of pipe. You can have subsequently higher notes played with the same fingering. How many of you have ever seen a military bugle before? Seen it, right? Good, a whole bunch of you. Are there any buttons on that? No. It's just a bunch of wrapped around pipe, right? One length of pipe. Can he only play one note? No, he can play a whole bunch of notes. How does he do that? Well, there's a whole bunch of different frequencies that I can produce and still align an antinode with the end of the length of the pipe. I just have to change the frequency so I align them perfectly. I can do that with a trumpet too. I won't touch the buttons at all. I didn't touch anything. All I did was change the frequency of the buzz, and it made a whole bunch of different notes with the same length of pipe. We're going to talk about how those are all related to each other later.
Can you play that song, When the Saints So Much?
There will be no performances today.
You and Mark will sing. Mark and I.
No. Something really weird happens with closed pipe. The closed pipes are a little bit more complicated, only because of what happens when a wave hits a solid barrier. You guys kind of learned this already. Remember when we did the Slinky Lab and you sent the pulse down to your partner? When it hit your partner, what did it do before it came back?
It flipped.
It flipped over. It flipped over. So it went down this way, came back going the other way. Well, when we have that closed end here, we have to say, all right, so but it's going to hit the barrier. What's it going to flip and back? So the first node isn't going to at half like it did over there. How much of a wave is this? It's only a fourth. So the first antinode actually happens. This is going to be a lower note, right? The fundamental frequency for a closed pipe is going to be lower because you've got that flipping that happens on that solid barrier. Does everyone see that? So the node happens the surface where it's reflecting, it reflects, and then your antinode will happen at 1/4 lambda. Looks like this. So for open pipes, this was the picture. The length of the pipe is equal to half of the fundamental. That's the lowest note. That's a relationship that you should probably have up here. And we're going to use it tomorrow, by the way, in the lab, where we're going to use the resonance in pipes for our lab tomorrow. Questions with anything that's on here? All right. So then for a closed pipe, what changes? Well, because of the reflection on this boundary, the antinode that's aligned, will happen when you only have a fourth of the overall length of the wave in the pipe, and so you end up with the relationship being L equals 1/4 lambda. Does everyone see how easy these little equations are? It's basically saying, if you know one, you know the other one. It's not a 3-variable equation, it's a 2-variable equation. So if I know how long the pipe is, I immediately know what lambda is. If I know if I know what lambda is, I can figure out what length of pipe I have. Now, this also goes into V equals F lambda, so you know I can draw connections to other equations, but at the same time, this particular equation is pretty simple. So if I have a pipe organ that is a closed pipe organ, and the length of the pipe that I'm dealing with is 1/2 meter, what's lambda? I'll repeat the question. I have a closed pipe organ that I'm installing a pipe for that pipe organ that is 1/2 meter. What is lambda? It's 2 meters. So now I know the wavelength. I could have asked you a question that would have been a little bit more complicated, right? I could have said, the length of the pipe is 1/2 meter. What is the frequency, the fundamental frequency of the note produced by that pipe? Does everyone see that you can get there? First, you go ahead and you do the 2. Okay, lambda's 2. Then I got to go into V equals F lambda to get the frequency. Right? You can get the frequency because the speed of sound and air, and by the way, usually it's specified, but if you have a problem on the AP exam or on our next exam where there's no temperature specified, then you get to assume that you're at room temperature. So the speed of sound is 343, right? And then you've got your lambda now. We figured that was 2. So from that, you could get your fundamental frequency. Pretty simple. Everyone understand? Fundamental frequency is the lowest note that you can get out of that length of tube. So what happens when you're not aligning the lowest note? What happens if you're going to squeeze more wave into the pipe? Does everyone see that all 3 of these are the same length of pipe? And all of these are cut off as the same length of pipe, right? In the first case, I'm showing you the fundamental. Here it's open on both ends, so the fundamental happens at 1/2 lambda. Here it's closed on this end, so the fundamental happens at 1/4 lambda. Now, if I squish a higher frequency wave into the same length of pipe while still aligning the antinode with the end, I get a new resonance that's at a higher pitch. Right? Did you guys notice? And, my trumpet playing skills are way, way in my past, but you notice that there was that lowest note, and I was able to go up above it, right? That's what's happening with these harmonics that are often referred to also as overtones. When you're figuring out what the overtones are, what you're doing is you're just smashing a higher frequency wave into the same length of pipe. So you're aligning a new antinode, essentially. So here, how much of a wave is this when you're going from here to here? How much of a wave is that? That's a whole wave, isn't it? Here it's 1/2 a wave. Now, so this is 1/2 lambda. Here I'm at lambda. How many is this? There's 1 and another 1/2. So 1/2 lambda, lambda, 1.5 lambda. What do you think the next one's going to be? 2 lambda. 2.5 lambda, 3 lambda. So every 1/2 lambda, you're going to get a new antinode, and you're going to get a higher frequency overtone. Pretty cool. Mathematically, it works out pretty cool, and also musically, it makes sense. So there's going to be, all of you have heard the term octave before, right? Even those of you that aren't in music. Well, mathematically, that makes sense with this whole overtone thing, too. So the physics of music, the math of music, and then the sounds in music all kind of fit together really, really nicely. It's kind of cool. And I do have a slide to show you that. Let's go over here. For closed loops, first antinode happens. If I go, the next antinode I could line up is what? When the wave is representing how much of a wave? Well, here's half. How much more is that? Another quarter. So what is that? 3/4. What? And a fourth or 5/4. What do you think the next one's? So I did 1/4, 3/4, 5/4, 7/4, 9/4, 11/4, and so on. So it's still going to be every half lambda, but the first one doesn't start at a half, right? It starts at a fourth. So when you're adding a half to a fourth, you're going to be on odd fourths. So 1/4, 3/4, 5/4, 7/4, 9/4, 11/4. Your antinodes are going to be off by that quarter because of the reflection off the solid barrier that made that first antinode shift forward. Does everyone understand that? So closed is a little bit more complicated because you've got the quarter going on instead of every half or whole wavelength. All right? So those are the overtones. Now, there are mathematical relationships that you can learn to figure out overtones. I don't think it's going to come to this on the AP exam, but I figure you could easily see what's going on. Isn't this what we just did? Fundamental was when you plug in a 1 over here, so it's just half lambda. Then the first overtone was when you put in a 2. 2 over 2 is lambda. Then 3/2 lambda when you put in 3. 4/2 lambda, which is 2 lambda, and so on. And then over here, you don't get to just put in every integer, right? You have to put in the odds, because I told you we were on odd fourths. 1/4, 3/4, 5/4, 7/4. So these equations basically just mathematically describe what we talked about verbally. Does everyone agree? All right. So I found some pictures to kind of lay it all out at once. So there's your fundamental frequencies. Those are the lowest notes that you can play out of any length of pipe. Any musical instrument, when you're maximizing the length of the pipe and you're going to put the most spread out wave in there that you can. For an open pipe, it happens at half the wavelength. For a closed pipe, it happens at a fourth the wavelength. So the first overtone's going to happen when you've got a full wavelength. First overtone for closed at 3/4, 5/4, 7/4. We already talked about these, right? And now you can see why. Because you can see that you're going to take these yellow pipes are exactly the same length, and we're just changing the frequency of what we're putting in there to get a new antinode to show up. Isn't that cool? That's how all of these things work. It's amazing. And all of these overtones become incredibly important to people that know how to play, right? Because then it becomes a matter of, all right, I'm not changing the length of the pipe to make this note, so I have to have the control with my playing to change the overtone that I'm going to call up. Does that make sense? And those of you that play a brass instrument especially, you guys know exactly what I'm talking about. So you know that there's a variety of different frequencies you can play with that specific fingering, and you have to have the control with your mouth to call on the right one while you're playing. And the faster the music's going, the more control and accuracy it takes in what you're doing to manage that, because you don't have a lot of other options. There's only certain ways to get each of the frequencies you're looking for. And that's where the skill part of playing an instrument comes from. Right? It would be easy if all we had to do is press the right button and out comes the right thing. Well, easier, because that's kind of how a piano is. That's not that easy either, but it would be easier to generate notes the right way if all you had to do is press the buttons. But then when a piano player learns how to do that and do it well, they're not going to press one button at a time, right? That's why I always call, I wished as a kid that I studied the piano, because I really feel like you're the one-man band then, because you can play you can do all the parts, and have the ability, because you have all these fingers, to play multiple notes at the same time. As an old trumpet player, you're doing things one at a time. You have to do one note, then go on to the next note, and so every instrument has its own complications, I guess. Anyone have any questions with the different overtones that you can produce in the pipe? Because next slide, we're going to learn how to figure those out. And it's not hard. So this just helps us to define what overtones look like. So overtones are mathematically related and musically related to each other, and they are just integer multiples of the fundamental. So the first overtone is just the fundamental times 2. The second overtone is the fundamental times 3. Third overtone is the fundamental times 4, and so on. So if you know the number of the overtone that you're looking for, you take the fundamental and you multiply it by that number plus 1. Isn't that what I just did? First overtone is fundamental times 2. Second overtone, so overtone 2, is the fundamental times 3. So we look at this little equation, which you won't find in a book. I just wrote it up here to help you to remember what we're talking about. The frequency of the overtone you're looking for. It's equal times the number of that overtone plus 1. So if I'm looking for the 31st overtone, which I don't know why you would, because that would be like probably super high frequency, right? But if you were looking for the 31st overtone, it would be the fundamental times 32. Right? You're just going to add 1 to the overtone that you're looking for, multiply that by the fundamental. So how do you do problems like this? Well, if you are relating the length of the pipe to lambda, right, that lambda will help you to find the fundamental frequency, because you'll plug that lambda into V equals F lambda, get the fundamental frequency. Then to find the overtones is easy, because you're going to just look at what overtones you're looking for, take that fundamental value, and multiply it by that n plus 1. Does everyone understand? Now, why are we learning this? What's the big picture of this as it relates to maybe like some musical stuff? Well, the first overtone, when you double the frequency of the fundamental, you will be exactly an octave above. So it's not by magic that those sound related to each other. They are very much related to each other. One is exactly twice the frequency of the other. Think about those of you that are my music buffs in here, and think about your music theory, right? You learned probably that middle C is 256, right? If you go to 128, which is half of that, you're at low C. If you go to 512, guess what? You're at the next C. So they are related to each other mathematically, aren't they? And so the first overtone has that relationship to it. If you go to the second overtone, it's the fifth above that octave. So the second overtone, which is the fundamental times 3, gives us the ability to understand how mathematically some of these other notes make sense, right? A fifth, for those of you that aren't musically inclined, is the fifth note of the scale, which when you combine it with the root note of the scale, 1 and 5 are the basis of a major chord, right? So they sound nice together. Make sense? So, and so on. You know, we're not going to do a music theory lesson here. We're just going to talk a little bit in generalities about the fact that overtones not only are multiples of the fundamental, they also help us to make sense of what sounds good together. And we've been able to hone that very, very accurately as time has gone by, so that now when the piano tuner comes over, he's looking for very, very precise numbers for your tuning. Does everyone agree? They got a lot of special instruments to make sure that your piano's in perfect tune. Okay. How does all on a closed-ended instrument? And does it work the same way? What makes an instrument like this make a sound? Vibrations. all wave energy comes from vibration, right? So what's vibrating? The strings. How do the strings make the wood vibrate?
What the little thing?
What's with this little thing?
Yeah.
Okay, yeah, with the bridge. So the strings are held tightly from the nut to the bridge, and this thing's designed to shake, and it's attached firmly to the thing that actually makes the sound project. When these vibrate, the air inside, and by the way, does this thing really need this hole? Will it not make a sound if there's not a hole? It'll make a sound, right? This is what it really needs, right? The more accurately your soundboard can project the sound and resonate with the vibrations of the strings, the better the instrument is. So we get this whole chamber of air inside here vibrating. It's going to shake the entire body of the guitar and project the sound outward. Acoustic guitars, especially acoustic violins, acoustic pianos, they're going to be as good as their soundboard. And the more expensive they are, the more, the better the soundboard is, the more expensive they're going to be, the more accurate they're going to be. So when I play a note, if we muffle the soundboard, it won't sound nearly as loud. And you guys have probably heard, like on an electric guitar that has a solid chunk of wood that everything's on, it doesn't sound nearly as loud and as bright, does it? This, they thin out the wood everywhere and hollow it out and give you an air chamber because they want it to acoustically project sound. We're not going to use electricity and a signal and magnetism and all of this induced current stuff that you'll learn later to make the signal. We're going to just try to get it to vibrate acoustically. Now, why do they have different thickness strings? Why do they need those? Think about inertia a little bit. Why does that one sound so much lower than that one? And it's thicker and more massive, right? I brought a classical guitar here, so these lower strings down here, they don't look really, really thin, but they're made out of nylon. These are made out of metal, right? So as this string is trying to go back and forth, which one's going to have a greater resistance to changing its direction? The thicker, heavier one or the thinner one? The thicker one, right? So the thicker, heavier strings are going to sound lower. They're going to vibrate back and forth at a lower frequency than the thinner ones. How can I make it so that even any given string could sound higher or lower? I can increase the tension, right? So I can turn these, but it would be really hard to play the guitar if the way we were changing our notes is by turning. Could you imagine how fast you'd have to be at turning the knobs? That would be hard. So that's one way, though. You're right. So we can increase the tension, and that does have some variation in the notes that are played. What's another way? I could shorten the amount that I'm allowing to vibrate, and that's exactly the premise behind all of these stringed instruments and how they're working, right? The amount of mass that I'm moving back and forth is going to directly affect the frequency of the vibration. If I shorten up the amount of mass that has to go back and forth, it can go back and forth more quickly. So as I go up the neck, the frequency of the notes is going to go up because these strings getting shorter. So there's two ways on the instrument that they're using inertia and frequency and how they're related to each other to change the notes. One is to change the thickness and the amount of mass total. And then the other is to change the amount of the string that you're actually allowing to vibrate. And that's why we have this fingerboard here. On the piano, you can't do that, right? So they have to have keys assigned to each. So they do have different mass strings, right? Different thicknesses and different, even slightly different tensions. And then they also have different lengths. That's why the piano has that kind of weird shape to it, right? There's some strings that are longer, some that are shorter, some that are thicker, some that are thinner, and usually, for any given note, there's more than one string. It's important. Why do they think they do that? Because a piano is like this big thing. Some of those strings for those really low notes are kind of big, and that soundboard is really big and heavy, sometimes even mounted in like a cast. So they need a little bit more energy to vibrate the larger soundboard, and so they'll usually, when you hit the hammer onto a string, it's usually going to hit more than one. It's kind of cool too, because then if you break one, especially in the higher notes, you can the piano will still work until you get the piano tuner guy to come and put another one in. Anyway.
Yeah, come on, keep going.
No, I'm just a teaser. All right. Two other topics to cover. So, first of all, does everyone feel pretty comfortable? Like, if I give you a length of pipe and the temperature in the room, and I say, tell me, this is a closed pipe scenario, tell me what the fundamental frequency is in the third and fourth overtones, that you can do that, based on what we learned today. So for closed pipe, the fundamental lambda is, so you would just do the length equals half lambda, find lambda, go into V equals F lambda, find F. Now you've got your fundamental frequency. It's 2 steps. If it's an open pipe, instead of using fourth lambda, it's half. That's it. So I give you the length of the pipe. You use that to find lambda. You use the velocity of sound and lambda to find the frequency. You've got your fundamental, and boom, off you go. It's that simple. It's just that's the first time you're learning it, and we're learning a lot of things today. So I want to make sure that you understand that. Now we've recorded it. You can go back and listen to what I said and then be able to hopefully run through it a couple times. Should be able to get it. I will be checking that because I'm going to give you a problem very similar to what I just said. Now, if instead I give you lambda, or I give you the fundamental frequency, or I give you one of the overtones, and then I ask you what length of pipe must it have been, you go the other way, right? You go from the frequency to V equals F lambda to get lambda. Then you know if that's the fundamental frequency that you can go right into the length, or you have to unravel what the fundamental frequency is and so on. So there will be a problem like that on the exam, for sure. And there may even be one that's going to mimic what we do tomorrow in the lab, because we're going to use a closed pipe scenario in the lab tomorrow. All right. So now we're going to move on to the 2 special topics. The first one is the Doppler effect. The Doppler effect describes what happens when either the source of a wave or the observer of a wave, or both, are moving. Okay? So, an example. The train goes by, the whistle's going, and the pitch of the whistle of the train appears to be bending and changing as it whizzes by. You get the, you know what I'm talking about, right?
One more time?
One more time? Okay. There it is. So, that sound is deceiving, isn't it? Is the sound really changing at the source? It is not, right? The Doppler effect, that's why we call it an apparent shift in frequency, right? It's a frequency we experience as an observer because of relative motion. Oh, I don't want to do that. I want to do this. So, if things aren't moving, then life is easy. The tuning fork here is producing a disturbance. The disturbance is very uniform and goes into your ear, and you hear what the tuning fork is doing. Does everyone agree? Now, what happens when the source, so here we have the same scenario. The source is creating the wave's going, and then this is the response of the listener. You see how the blue ball is going up and down with exactly the same frequency as the red one? Okay. Now, what happens if we move the line that the blue ball is on towards the red one? Does everyone see how much faster The blue ball's going up and down now. It's as the two approach each other, the frequency appears to go up. Why is it going up? Well, you are approaching the wavefronts. You're helping the wavefronts get to you quicker. As they come at you quicker, the frequency with which you are hearing the changes in pressure goes up. If that frequency goes up, it appears to be a higher note. The pitch goes up. If instead the line that the blue ball is on is moving away from the source, look what happens to the oscillations now. As you move away, you get the lower, right? It's slowing down. Why is it slowing down? Because we're moving away from the wavefront. Now, Phil asked a question the other day about, so if a sound is happening and you can get out in front of it, will you not hear it? Well, I got you covered. That's exactly what happens. So in this scenario, if the line is moving as fast as sound, then it doesn't move up and down at all. So you don't hear it. There's no disturbance because you're moving at the same speed as the disturbance, so there's going to be no disturbance getting to your ear. There's no frequency if you are matching the speed of the sound. If you go beyond it, that is the perfect sound. If you can go beyond the sound disturbance that you're creating, then you break the sound barrier, is what we say, and you are getting out ahead of the noise that you're making. So the disturbance is behind you. It's in your wake, we like to say. It looks graphically like this. So the red dot represents you making the disturbance, and that conical shape of really, really loud noise, right, of air being, mixed around in a very turbulent fashion is behind you. Now, we have aircraft that can do this, right? That can go Mach 1, 2, 3. They are not allowed to do that in residential neighborhoods down low. If they did, they'd be blowing out our windows, right? Because that disturbance, you can see as it kind of fans out, it weakens. But you can see right near the source, see how tight that pattern is, how strong that disturbance can be. As they're flying by and they whiz by you, they can, shake the foundation of your house pretty good to the point where it's not going to rattle your windows. It could even break your windows. So only in case of emergencies would, you see military planes flying at those speeds, close to the ground in areas that are highly occupied by people. Questions with what we learned today? Heck of a last day. There's a lot of stuff, but nothing hopefully terribly troubling. You got a PDF copy of all of the slides that were on the board today. I sent to you. I also sent it to you as a notebook file, minus a couple of pictures that I enhanced. But you should have all of the documentation that you need.